This is Software Engineering Radio, the podcast for professional developers, on the web at SE-Radio.net. SE-Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE-Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
Hello, this is Charles Anderson for Software Engineering Radio. Today we are talking to John Wilkes about Google's Borg system. John has been at Google since 2008, where he is working on cluster management and infrastructure services. Before that, he spent a long time at HP Labs, becoming an HP and ACM Fellow in 2002. He is interested in many aspects of distributed systems, but a recurring theme has been technologies that allow systems to manage themselves. Is there anything else you'd like to add, John?
No, that's good. Thanks. I just hit my 7-year anniversary at Google and still having a blast here.
Oh, most excellent. So, at a very high level, what is Borg and what does it do at Google?
Great. Well, let me first start out by saying that we have to officially say the system that is internally known as Borg to keep the lawyers happy. But now we've done that once, we can carry on. Borg is the system we use to manage our internal clusters of machines. Its primary purpose is to serve our internal users, the folk who write things like Gmail or Google Docs, and give them access to the resources they need to do their work, which is what they need to do in order to be able to do stuff and support us in the outside world. So Borg is basically a scheduling system. Give it some work, it decides which machines to run that work on, and picks up the pieces when one of those machines needs to be taken out for an operating system upgrade, or we discover that things don't quite fit the way we thought they would fit.
Okay, yeah, we'll talk a bit later about the scheduling. Without the benefits of a whiteboard to draw a picture or something, can you please tell us about the players in the Borg landscape?
Sure. So let's start on the physical side. So I like to think of, we have a fleet of machines that is scattered across the globe. Those machines live in data centers. Data centers typically contain one or more buildings. A building will typically contain one or more clusters. And a cluster is a set of machines with a high-speed network between them. Think order of magnitude 10,000-ish as a median-sized cluster. And those machines live in racks, etc., just in sort of the standard way that you would expect a large-scale data center to be built. On the software side, what we do is we take a cluster and we divide it into one or more cells. And a cell is a group of machines that are managed as a unit by one instance of Borg. So typically each cluster has one large cell carved out of it. Sometimes there's a few additional ones for testing purposes, and occasionally you'll take one cluster and sort of subdivide it into a larger number of cells. But most large clusters have a large cell as part of them. A cell is managed by Borg, which has a couple of different components. One is Borg Master, which is the central component that looks after the state of the whole cell. And then also on each machine in that cell, we run an agent we call the Borglet, which is responsible for keeping tabs on the various tasks and containers and processes and things running locally. I've used the word task here. A task is just a Linux container running some application, and we group those into an entity we call a job, which is just a collection of basically identical tasks. And when you submit a piece of work to Borg, you say, here is a job containing 400 copies of this task. Please, could you schedule it and place it and keep it up? Those kinds of things.
Okay, yeah, that's pretty good coverage there. So you touched on a couple of examples of programs that run under Borg. What programs do run? You mentioned maybe something like Gmail. Is it just things that run at scale, things that are...
Actually, pretty much everything that we do runs at Borg. There's a few special case exceptions, but to a first order, think of everything that we do runs on top of Borg. So every single externally facing application that you can see, almost all of those will be running on top of Borg. And then, of course, you can imagine there's a bunch of behind-the-scenes stuff, analytics, MapReduce jobs, data analysis pipelines, monitoring. Those all run on top of Borg as well.
Okay. So it's almost sort of the operating system of Google.
Exactly.
Okay. Since our audience is primarily software developers, I want to talk a little bit about the programmer's perspective. How does a programmer writing an application to run under Borg, does Borg impose any limits or anything like that, or is it a special paradigm or anything?
So the idea we have of Borg is that it's a sort of universal underpinnings for pretty much whatever you would like to do. The assumption is that you're going to be running a Linux task on a sort of production version of Linux. We have our own internal production versions that we sort of develop and enhance over time. But that's basically the assumption, right? If you can run in a Linux container, you can run on top of Borg. We don't particularly constrain the programming language. We support particular ones internally, but there's actually a wide variety of languages that get used by different people. The language you write your program in, you build a binary using our build system. You might have heard of that sort of thing called, externally it's called Bazel, internally we call it Blaze. The output of that is a binary that can be run on top of Borg. We have lots of libraries that get to make things easier if you do certain things in a particular way. So there are conventions and protocols we use internally. If you do it this way, it will be easier, but you can actually write stuff your own way if you really want to do that. So that describes the program. And then you also have to tell Borg, I want to run that program. And to do that, we provide a little sort of an RPC interface to Borg where you say, submit my job. Most people don't use the RPC interface directly. They go through a couple of different systems. The most common probably is a thing called the Borg configuration language, BCL, which is a little language where you basically get to describe, it's basically a protobuf description. You provide a set of properties about your job as sort of key value pairs, and BCL is a language that lets you write those things. In a straightforward, simple case, you can write a description for a job in a dozen lines or less, but you also have a little programming language available to you. It has Lambda functions built in, so some people can and do write sort of dynamic stuff based on where you land in a cell and what the properties are of the computation you're trying to do. So it will compute values that get entered into the job descriptions. There are other people who prefer to do it in a programming language like Python. So we have a wide variety of different approaches where programmers can provide the configuration data. MapReduce jobs, for example, you describe a MapReduce job and the MapReduce master goes off and generates behind-the-scenes job requests to the rest of Borg on your behalf. But the real thing to take away from this is, as a programmer, you get to write programs pretty much the way you like, and then you get to run them at whatever scale you think is appropriate. A story I often tell when I'm describing Borg to the outside world based on the Borg paper is that at one point we decided we needed to rerun all the experiments we'd done, which was sort of doing some performance evaluations and comparisons. So we pressed the rerun all the experiments button and went away for lunch. And when we came back, I asked the question, great, what did that take? How many things were we running at once? And the answer was we had burnt up to a maximum of about 200,000 CPU cores allocated to our experiment, and nobody cared. That was the kind of thing that Borg makes possible because those machines were available, people weren't currently using them, so we were able to jump in and take advantage of them. That's the kind of productivity that we just didn't have to worry about that stuff that we as Borg developers are trying to make available to our internal users. Our goal is to help them focus on what it is they want to do and not worry about stuff like, can I get resources in the right place at the right time?
Well, yeah, I remember the number of the 200,000 cores from the paper, and that is impressive to, if you will, almost by accident happen to be using 200,000 cores, and like you say, it not even causing a big problem for anyone. With the Borg configuration language or the API for it, is that a static thing? Do I say, here, I want 1,000 instances of this, or is it a dynamic thing once my job is running? If I see that, it's Christmas is coming and everyone's hitting the system and I need to double my number of instances running, can I do that?
Absolutely. So the way to think of it is you submit a description of what you want to be true, which is a job description, like I want 1,000 instances now. You send that to Borg and it says, great, thank you, got it. And then it will start working on making that happen. You can come along later and what we call update that job description. You can change the number of tasks, you can change parameters on the tasks, you can change priorities, you can change the sizes of some of the things. Excuse me, you can change the binary they're running. But those are just updates. You can do them, some of them are non-disruptive. They just sort of get pushed out and no changes happen. Some of them, for example, if you add extra tasks, that's the existing ones stay up. You just add extra tasks, the job just gets bigger. Some of them are disruptive and you actually have to restart things. For example, if you push out a new binary, then yes, the old ones have to stop at some point and pick up the new copy. But there's a range of different behaviors and those things are all well documented. But yes, the system will respond to changes that you make as you make them. And the standard answer will be, great, thank you, got your request, I'm working on it. And sometime later the system will ideally have responded to and have made true the request that you asked of it.
Okay. And presumably also if you're pushing a new binary and it does require restarting, it can do something like a rolling restart, if that's applicable?
Exactly. We have ways of saying, I want you to start at this end and work your way up. And if you discover that's not working well, you can say, no, hold on, let's go back. So we have a sort of present state and a future state, and an update actually says, it's sort of like almost a lightweight transaction. You say, start moving towards the future state. And if you decide you like it, then you can basically commit it to say, okay, great, make the future state be the one. And if you decide you don't like it, you can say, nope, let's go back to the previous state and sort of undo the changes. And then they will get reversed. They will, it'll go back to the previous state and you can pick up and carry on. So we use that often for sort of rolling out a new version of stuff so we can canary it and watch it happen and make sure that we haven't accidentally broken something. It's really useful to be able to go back to a previous state that you knew that worked.
Right, yeah. The canary release kind of thing was my next question, actually. Okay. If I'm going to write an application for Borg and I'm going to distribute it across hundreds or thousands of machines, and I don't really have, I assume I'm not picking and choosing individual machines, Borg is for me.
Correct.
How do I debug something like that? What facilities does Borg provide to help me get a handle on what's going on with my program, what's working, what's not working?
Great question. We provide a whole bunch of different, couple of different things, right? Monitoring. There's a lot of monitoring that takes place, sort of keep an eye on what your job is doing. Most applications, almost all applications, will link in sort of by default a little web server which publishes information about things like RPC requests that it makes or are made to it. So you can sort of go poke at it and retrieve information from it about what's going on, how fast it is going on, how long it takes to do, how many of them are happening of different kinds. So that information is gathered up and made available through monitoring systems. Those monitoring systems provide dashboards so you can look and see, well, how many of my tasks are up, which ones are healthy, which ones failed, why did they fail? Let me go find all the logs of sort of standard error and RPC logs if necessary. You can drill down into those things. And we provide a sort of a UI which is based around the web, of course, and you can sort of start at the top of the fleet and drill your way down from the fleet as a whole to an individual cell, to job that you're running or a set of jobs for a particular user, to a particular job, to a particular task in a particular job, and go actually open up the error logs for that task. Or you could have a view which says, let me collect all the error logs across all the tasks of a job. And so we provide that monitoring information, little graphs of how much CPU is being used across time, how much memory is being allocated, how much is being used. All of those things are part of the system that we provide our users to try and help them understand what it is their jobs are doing.
Excellent. And I can imagine that the volume of that log data would be pretty substantial, and maybe there's other Borg tasks for doing the equivalent of a grep through my logs if I'm trying to track something down across 1,000 machines.
Exactly. So the monitoring jobs are actually things that run on top of Borg. They sit there high priority, so they get access to resources when they need them. And they push out dashboards. Those dashboards have query engines built into them. So there's a fairly sophisticated set of monitoring stuff that's been built on top of the Borg ecosystem. So yes, that's one of the ways we make life easier for our developers.
In addition to programmers, Borg also, another class of users of Borg would be the site reliability engineers who are ensuring that my program, or working with Borg to make sure that my program's running and whatnot. What kind of features does Borg provide for them?
Well, the first thing to note is that the SRE teams actually get access to the same information as the developers do, and vice versa. So they can both share stuff and try and debug things together if they need to. They tend to build additional dashboards on top of the underlying data sources that both Borg and the monitoring systems that are on top of it provide. To put things like SLOs and alerting rules and triggers, and paging people if things are going really bad, or just pointing out that they should pay attention if not. So yes, the same kind of visibility. We have a model that a lot of the stuff is visible to anybody who's qualified and permitted to get access to the monitoring information about what's happening. So that makes it actually quite possible for anybody to go in. And they specialize in building tools on top of the underlying ecosystem parts to do things like rolling out and to push out a new version and to make sure it's working right and to test it and to probe it every now and again to make sure that it's actually all up. For example, the storage system, right? You want to make sure that you can access all of your bits. Well, the way you have to do that is you have to go touch some fraction of all of your bits to make sure the storage system as a whole is up and running. So they build things like probing systems that run as jobs on top of Borg. So they are both customers of Borg and sort of mentors of things that are running on top of it. And then, of course, we also have the Borg SRE team, which are spectacularly good at keeping the thing up and running. And they are, I like to describe them, I think of as operators with PhDs, sort of one way to think of these incredibly capable people who understand interrelationships and interactions at very large scale between complicated systems that are in dynamic flux all the time. And they're spectacularly good at what they do. And, we provide what we can in terms of tools to help them understand what's going on.
Okay, so for the programmer, it gives me the ability to write my program and have it run at scale. For the SREs, it gives them the ability to ensure that my program's running at scale. And I suppose also it's a scaling function for SREs in terms of allowing fewer of them to do more work in terms of managing tens of thousands of machines and whatnot.
Exactly, and I think one thing I want to stress about the SRE team is that they don't just operate systems, but they also program and do engineering around automating a whole bunch of the stuff that, if you do it twice, for heaven's sake, let's automate it, because people make mistakes if we let them do it. So they're in the process of building layers of software and tooling on top of the underlying systems that make both their life and the life of their internal customers better.
Right, and you mentioned that they're building on top of Borg also, so everyone's playing with the same toolbox, and everyone has a vested interest in making it the best it can be.
Exactly.
So let's kind of move into a little more details about what Borg is doing. At the highest level, what are some of the objectives it's trying to meet? I guess we sort of touched on that a little bit, at least from the SRE angle, but in terms of scaling and whatnot?
Yeah, so I think at the highest level, Borg's goal is to minimize the amount of time that our developers and the SRE team supporting them spend thinking about infrastructure, right? They have better things to spend their time on and do development for. So we'll do that for them. We'll worry about infrastructure. We'll worry about provisioning enough resources in the right places of the right kind. We'll worry about coping with failures on their behalf. We'll restart stuff if it falls over and pick it up again. And at the same time, we try to do this in an efficient a fashion as we can, right? Once something stays up, then we come back and ask the question, great, how can we make it more efficient? So how do we act as good custodians of Google's investments in hardware and machines and networking and stuff like that to make it maximally effective in delivering end results to our end users by trying to make sure we don't have stuff that's lying around idle when we could be doing other things with it? Sure.
Efficiency in a word there.
Yes, so I tend to say availability first, efficiency second.
Right. An unavailable efficient system is pretty useless.
Yeah, exactly.
So one of the functions of Borg is scheduling. And I believe you mentioned this before. What exactly is it scheduling?
Yeah, the unit of scheduling for Borg is a task or a container. Now, we actually run tasks in containers, so from Borg's perspective, they're basically the same thing. So this is a Linux C group, so it has a capacity in terms of amount of memory, and amount of CPU cycles, amount of disk space, amount of disk traffic, and a few other things as well. And it has these sort of multi-dimensional rectangles, if you want to think of it that way, that it is trying to pack into machines which also have multidimensional properties about how much memory they have, how much CPU they have, and stuff like that. So those are the units of placement scheduling. Now, we collect, to make things easier, we provide collections of tasks or containers. So a collection of tasks is called a job. We also have high-level collections we call allocs, which basically are containers, a set of containers, and they just reserve space, right? So you put aside some memory and some CPU cycles, and then you can run a job or a task within one of those alloc instances. We can talk later about how that's useful, but it makes it easier to provide things like high resiliency log management on top of a complicated system. And what Borg does is it schedules those outer level containers, whether they're an alloc instance or a task that's running by itself, so our top level task we call it, and it packs those onto machines in an expeditious fashion in a way that makes sure that things like availability considerations are taken into account.
Okay, so the efficiency of that packing the most items in a given number of machines is sort of the overall efficiency, and then you mentioned availability, so that we don't pack everything all on one machine or in one rack or something like that, right?
Exactly. So, for example, by default, Borg will spread the tasks of a job across multiple racks, because that increases your resiliency in the face of, let's say, a top-of-rack switch breaking.
Right. And then presumably there are other kind of placement things that one could declare in the configuration language.
Oh, indeed, yes.
Okay.
So the last time I looked, there was something over 200 parameters you could specify in a description for a Borg job or a Borg alloc. There's lots of things you can constrain. Some of these are placement constraints. You can say things like, don't have more than 2 of these tasks on one rack. You can say things like, I need to be running on a system which has this version of the operating system because I need some parameters it has. I need to be running on this particular kind of hardware because I'm relying on some features the hardware has, or I need to avoid a bug that was present. There's a whole raft of these things, and there's lots of control over sort of fine-grained placement of CPU threads onto CPU cores, which gets passed down to the Borglet and then eventually to the kernel, and so on and so forth. And each of these things has evolved over time, and we've built up a pretty broad library of stuff that gives people who really need it very fine-grained control of exactly what happens. And people who don't need it, they actually don't have to specify most of those things. The system will just do something plausible, even if you don't say very much.
And the tasks are running in containers, and those containers are maybe not Docker containers exactly, but they're built from the same primitives, right? Exactly
the same basic idea, right? It's a Linux C group, which is a resource. It owns a chunk of resources in particular dimensions, like amount of CPU, amount of memory. We also put them in a little chroot jail, so they can't sort of break out and see bits of the machine they shouldn't have access to. Various things like that. So yes, it's the Docker container sort of notion is the external manifestation of this. We have been using much the same technology inside Google for about a decade now.
Right. Yeah, I think I heard recently that a lot of those primitives were developed either in part or full by Google and pushed into the upstream kernel.
Yeah, exactly. It's good for us and it's good for the community. We'd like to help to contribute in that way.
Okay. So in a cell, where are the various scheduling decisions being made?
Sure. So I mentioned the Borgmaster earlier, which is actually a central overseer for all the stuff that happens inside the cell. And that's also the place where we do the placement of the scheduling decisions. You submit a request to the Borgmaster, and it makes a choice about where things run. You can also go to the Borgmaster and get access to which jobs are running where. So some of those user interfaces I described are provided data that is the background for them by the Borgmaster. So it's a central point. This is different than some other systems which sort of make the scheduling the thing that gets distributed and done across all the individual jobs. We've chosen to centralize it, and actually, surprisingly, it has worked quite well. Occasionally people ask us, when you're going to hit a scaling limitation. And the answer is we come close to it every now and again, and then we do something to make the thing go faster, so the scaling limitation sort of evaporates for a while. So we haven't hit a hard limit yet. Clearly we will one day, but so far we haven't run into that particular problem.
Okay, and then at an even higher level, how does a programmer or an SRE go about choosing which cell to run something in? Is that a geographic type decision or something like that?
Great question. Actually, let me first inject a reason why we have these multiple cells. The first is to give people control over things like geographical diversity. Another is to give them control over sort of planned outages. We will do maintenance on a cluster, for example, or a whole cell every now and again. And we want to make sure that we don't take down both copies of your application if you put them in different cells. So we publish schedules that allow people to say, if I pick this pair of cells, they will not be taken down for planned maintenance simultaneously. And then the third reason is just to avoid error propagation. Right? An awful lot of outages in large-scale systems are caused by human error, and we want to put boundaries on the scope of the error that a human can cause. And a cell is a great boundary for that. Right? So you can take down a whole cell, but you won't take down the one next to it. There's a story, one of my SRE colleagues actually was trying to drain a cell to do some maintenance work, and he typed the command to do this and pressed enter and then went and checked the logs, and nothing had happened. So like any smart person, he does exactly the same thing again, and the same results are repeated. And then he looks more closely at what he'd done, and what he discovered was that he had mistyped the cell name and had taken down a cell, just not the one he meant. So those are the kind of errors that you actually want to bound in scope. So that's one reason that cells are actually very, very isolated from one another. They don't depend on one another for almost anything. So they can be brought up and brought down again independently of one another, and errors have some sort of bounded scope. Now, having been said, you now have a placement choice. If you're an application developer, you might start by saying, well, where are my external customers? Or where is my data? For example, you're a latency-sensitive app, you might want to have instances close to where the majority of your customers are. If you're doing sort of large-scale data mining analytics, you might want to be co-located fairly close to where your data lives. So that's sort of the first level thing, and from that you look at which cells are available in that region, let's say, or in that part of the globe, and then you go down and look and say which ones have space available in them, and then you go down and say, great, let me actually fire the request off to that particular cell and have it do work, and then inside the cell we'll find machines on which to do stuff. Now, we actually provide some tooling to help. If you don't really need to know in detail which cell things are running in and you've got a batch job, you can actually submit your batch job to a sort of global scheduler. We'll make these choices on your behalf. It'll look around and say, where is your data, or maybe just where are the free resources, and it will make the cell placement choice for you. So we do automation of things that occur at a level above Borg. So again, think of this as a base building block on which you can layer a whole bunch of other things. And then go down the other direction, when you eventually get down to a particular machine running a particular task, the Borget and the kernel collaborate between them to make sure that those tasks are being placed in a sensible way across all the different CPU cores, and the memory allocation stuff is done in a smart fashion. So it goes on, the ecosystem covers the whole range from global placement down to individual threads running on individual CPU cores.
Okay, and the Borg master is the master of one cell, right?
Correct.
Okay. You mentioned before about, in the context of log collection, the concept of prioritization. Mm-hmm. How are tasks characterized or prioritized? The paper mentions production and non-production. I would think user-facing and non-user-facing come into that.
Indeed, yes. So we actually have a fairly fine-grained priority system, small integers. 0 is low priority and goes up to 400-ish, I think. Most production jobs are run at one, so we have what's called a production priority band. All the jobs in that band have about the same priority. And the basic rule of thumb is a high priority job can preempt a low priority job. If we need the resources for a high priority job, it will run. It will even kick out low priority jobs. So typically we'll run user-facing jobs, especially latency-sensitive ones that have to respond to external requests for a web service or something like that. We'll run those at production priorities. And if there was a batch job that was in the way, well, the batch job is run at low priority and it will get kicked off. And that's fine because there's probably some other machine on which it could run on. So the idea is that we're actually trying to make sure that we do the stuff that is high priority, which is after all what high priority means, right? This is a business decision. And then if we need resources to run other stuff, they will fit in around the stuff that actually has to be up all the time. So sometimes this means that some batch jobs will get starved of resources because, we're busy serving front-end user requests, and absolutely that's fine. That's a very conscious choice about how we prioritize things.
Okay, and just to make sure I understood this correctly, lower priority jobs could be running and they can be terminated, preempted, and Borg will at some point in time maybe start them up again somewhere else or at some other time?
Exactly. Basically, they'll get put on the... so the preemptions actually happen at the level of individual tasks or allocs, so individual containers rather than whole jobs. And when a task gets preempted, it'll get put on a queue. Let's see if we can find another space somewhere else for it. And as soon as we can find space, we'll run it.
And then it's up to the programmer who developed that to then ensure that the task can be restarted and, I don't know, pick up where it left off or just start from the beginning again, something like that?
Yes, so it's both. You have to think about if I've got a whole job, right? If some fraction of it has disappeared because it's being preempted, can I keep going? For an individual tasks, you have choices. You can sort of pick up where you left off. If you're stateless, that's easy. You could choose to try and take a checkpoint every now and again to go and roll back to that. You could maybe hope that you'll be tapped on the shoulder. We will try to tap you on the shoulder and say, hey, we're about to preempt you. If we can, and we have time, we'll do that if we're permitted to. We aren't always able to it. For example, if the machine is running out of memory, we will just kill stuff. Right now, there's no chance to notify them. But often, probably the majority of the time, if you request a notification, you'll get it, and you'll have a few seconds to do something about it, like maybe dump some stuff out of memory if that's useful. So there are various different ways of recovering, and it depends on the cost of picking up and carrying on from where you left off as to which of those techniques you use, and all of them happen. But the fundamental principle is if your system is going to be up, you have to worry about parts of it being down all the time.
Right, especially at that scale. I mean, Google has published a number of papers and whatnot about failure is not an option, it's just reality.
It's just normal, yes. So, for example, internally we publish what we call an eviction budget, which is for every 1,000 tasks running for a week, roughly how many of them you should expect to get preempted. And you have to expect that as normal.
Right. And then possibly even, depending on the nature of your application, even be prepared to deal with abnormal as well, if it's something especially important and user-facing.
Yeah, so the model is that things can break at any moment. Whether they break because we needed to take the operating system down to reboot it for an upgrade, or the machine fell over, or the network stopped working, it really doesn't matter. If you're prepared for things disappearing at any moment, then you can also cope probably more gracefully with the things where you have some notice. But you have to assume that will happen because at this scale, it is always happening in the background.
Right. Okay. The paper presents a whole lot of data, a whole lot of numbers, graphs, etc., and whatnot. And it's not really practical for us to dive into those too much here, but were there any surprising or counterintuitive results that you found in your experiments? Things where you were expecting one sort of outcome and you were surprised to see what actually happened?
In some ways, yes. The first sort of surprising meta result to me was that nobody had asked some of the questions that I asked that we got answers for in the paper. So, for example, we run both sort of front-end user-facing tasks and back-end batch job tasks on the same machines. And the premise had been that saved resources. We didn't have to buy so many machines. And I asked the question, great, how many machines does that save? And we didn't know. So that was sort of surprising in some sense. So now we have some quantification, and we're pleased to see the result is positive. The other thing that sort of happened along the way was just getting appreciation for just how complicated this system is and its behaviors. We spent a lot of time running an experiment, getting an answer, looking at it and going, that's not right. And eventually we ended up wherever we could, we ended up doing evaluations in two different ways. So we'd build a sort of simulation model and actually try it out using the real code. And then we'd also build some sort of other path to the same data, maybe using traffic from our sort of log systems, and sort of see if we could cross-correlate the results to make sure that they were at least in the same ballpark. And that actually found quite a few bugs in the simulation work that we were doing. and occasionally in the analysis of the traces. So a lot of it is just getting a really good handle on making sure we understood how the system was behaving and what it was doing when we were tweaking in particular ways to explore different behaviors that it didn't normally do on a day-to-day basis. It's a very complicated system. It has a lot of moving parts in it, but I'm pretty confident when we were done that we had good answers. But they were mostly, roughly what we expected. There is this policy. It's there for this reason. Now we know just how much of that reason it provides, but we knew it was going to be positive. We just weren't quite sure how big the magnitude was.
Perhaps a lot of kind of quantifying what had become sort of standard operational procedures that perhaps had evolved from somebody's sort of gut feeling about how things should work and some experience running things.
So more typically, before we make a change, we'll actually do some internal studies and performance analyses, but those are typically done at a point in time across a set of workloads, which is a subset of the whole. One thing that was slightly surprising in sort of the review process for the paper was a few reviewers asked us, so can you explain why you have, why this cell is different than that cell? And the answer we came back with after a while, thinking about it for a bit, was actually no, and we don't want to. Right? Because we need to write software in the Borg ecosystem that is able to cope with whatever workload it is that our internal users throw at it. So if we end up trying to understand its behavior by specializing on particular workloads, we're probably ending up with a losing game. So we need to make sure that the systems we build are pretty capable of coping with a wide range of different use patterns. Because they're going to change over time, and as people move in and out of a cell, that'll be different. As people evolve their applications, what they're doing and what they're trying to accomplish is going to be changing as well, and we can't be too tightly tied to a particular workload.
Indeed, yeah, that makes perfect sense. Going back to the Borg master, we were discussing it as if it's a single entity, but it's not, because that would be a single point of failure, right?
Exactly, yes. So indeed, it in fact is replicated. We typically will run 5 Borg master instances. We elect one of them as a master. They have a data store which we keep all the state that they need to keep. We call it a checkpoint. It's built on top of Paxos. We use the Paxos algorithms to make sure that before a reply is sent back to a user, we have got a persistent copy in state of that state on disk. And even if that Borg master then disappears and another one gets elected, then we will be able to pick up where we left off. We collaborate with Chubby to store a pointer to which is the current Borg master. We use that for the lock management. So yes, the Borg master itself is designed to be a failure-tolerant system. Another example of that kind of behavior is that even if the Borg master itself, all the copies disappear, which occasionally happens, pretty rare, but occasionally, all the work that was currently running in the cell keeps going. There's no reason why it should stop. The tasks are running on their machines. The Borglet is still doing its stuff. If it can't talk to the Borg master for a while, it'll just keep doing whatever it was last told to do. So the system is designed with multiple levels of resiliency to try and keep going, even when the world around it is going pear-shaped.
Right. So it can continue on even if you can't tell it to make any changes yet, or any changes at the moment, because the Borg master is unavailable to make those changes.
Exactly.
Then how are the 5 Borg master processes placed or scheduled in the cell? Is that a recursive thing where Borg does it itself?
So when I said almost everything, this is an example where we actually place those replicas manually. So we choose machines with the right properties when you bring up a cell. And there are processes. The rate at which these things change is relatively small. Manual intervention is just fine. We can operate for a while with a subset of the 5. We prefer not to, but we can if we need to. So yes, we'll do manual selection of the 5 Borg master instances where they run, and then let the thing take off from there.
Okay. And then how is the Borg itself tested?
Mm-hmm. So we view the Borg master as just another distributed, replicated, failure-tolerant application. So all of the standard tricks you throw at a distributed, replicated, failure-tolerant application get thrown at Borg. We run it through a bunch of unit tests. We inject artificial failures. We do integration tests. We throw all sorts of nasty corner cases at it to make sure it will survive all of those. Every time we do have a bug, and we do have bugs occasionally, we will write a test case that will trigger that bug if it ever shows up again. So we make sure we don't do regression and accidentally reintroduce them by mistake. And once we got past that stage, then we'll actually run it in what we call a test cell. We'll actually bring it up, we'll throw workload at it. We have sort of synthetic workloads, some of which are derived from real life production stuff that happens elsewhere. We'll run that for a while. We'll do a sort of soak test in a testing cell. If that's successful, then we'll push it out to what we call a quality cell, where it's actually running real life production workloads, and we're just sort of monitoring and seeing how it does. Sort of occasionally we discover things because real life stuff is different than anything you might have captured in a test or in a standard benchmark. We'll catch a few more things there, and then we start a sort of cell-by-cell process of rolling it out across the rest of the fleet. Again, think of this as a canary, right? We don't trust it until it's proven to work, so we'll roll it out a couple of cells, look at it for a while. If that's good, we'll roll it out a few more. If they all start working well, then we'll start speeding up the process of rolling it out. So eventually we'll end up having pushed it everywhere. But at every stage, we make sure that if we decide we don't like what it's doing, we can go back to the previous version. We'll take a snapshot of the state before we push out a new version, so we can always revert to it. So we can always recover from various things that might go wrong.
And by the time you've finished doing the canary rollout, it's probably time to begin the release process again?
Even before that, yes. Sometimes there's more than one rollout going off at once. It's easier if there's only one, but sometimes we're trying to actually decrease the time between releases. Fast release with sort of smaller changes in them are probably a good thing. So we're in the process of making that happen much more quickly than it used to.
In the lessons learned section of the paper, there's a discussion of Kubernetes. And Kubernetes is an open source cluster management system developed by Google. What are some of the biggest things that you learned in working with Borg that are reflected in Kubernetes?
Great. So Kubernetes actually came out of many of the same people who developed Borg. So quite a few of the Borg developers are now Kubernetes developers. We tried where we could to echo the things that we found helpful in the Borg world and to try to avoid what we viewed as mistakes that in retrospect we wish we hadn't done in the Borg world, and do them in a different way in Kubernetes, hopefully better. So things we liked, right? Containers are definitely a great way of organizing applications. They make developers able to focus on their applications. They don't have to worry about things like operating systems and patching, bring them up to date, keeping the virus systems properly deployed, all that sort of stuff. It's a much higher level abstraction, much closer to where application programmers typically work. So that was a good thing. The second is this idea of a declarative specification. I want this to be true. And then what we call a reconciliation loop, which is comparing the external world with the statement about what you want to be true. For example, I want to have 100 copies of this task running somewhere. You put that into a loop and it says, well, how many are running? Oh, 0. Let me fix that. Let me place 100 of them and get it running. Great, do that, go back. How many, you want to have 100 tasks running? Great, how many running? 98. Let me fix that. There should be 2, that should be somewhere else. So that is a very resilient process in the face of failures, because you can always sort of pick up where you left off and carry on, because you have a state and you compare it with the outside world, and that difference tells you what you should do differently. I mentioned these allocation units. So in the Kubernetes world, they come as pods. A pod in Kubernetes is just one or more containers that get scheduled together onto a machine. We use them internally for things like building a very complicated web service and then sticking into the same machine a little tiny, super lightweight, super resilient, easy to debug, absolutely guaranteed to stay up thing that will extract logs from the complicated web service and push them out to a safe place on a distributed system. So even if the web service is going wrong in a horrible way, the log-saving system is going to keep running and pushing stuff out. And you want those things to be co-located because you don't want to have any complications of shipping stuff across networks and things like that. So that idea turns out to be useful for all sorts of different things. That's the simplest example, and we replicated that in the pods in Kubernetes. And then a couple of examples that things that didn't work quite so well. The first was this notion of a job as being a vector of tasks, where a task index in a job is a small integer. I'm the third task in this job. That's actually a nuisance, because what happens if that third one dies and you need to add another one? You have to reuse that slot, and you get sort of head-banging complications about how do you count, which ones do you up and do you reuse them and what have you. So we got rid of that in Kubernetes, and we went to sort of unique job IDs, unique pod IDs rather than a vector in a slot. And then the other thing we did was we generalized the notion of job from being just one single notion of a collection of things that is glued together into a very general notion, which is a combination of applying labels to individual pods or whatever, or containers or what have you, together with what we call a label selector, which is basically a query. It says, find me all the pods with the following set of properties. For example, front-end production version that's been up for more than a month. Just give me a list of all those things, and then maybe do something on them. So operations in Borg work on jobs. Operations in Kubernetes work on sets of pods chosen by a label selector. So it's much more flexible. So you can have sort of Venn diagram-like overlaps, and you have much more degrees of freedom. And they can be application and DevOps specified sets rather than stuff that's hardwired into the system. Some things we liked is the idea of being able to have sort of small miniature services. Borg is a bit of a monolithic ecosystem. Even the Borg master does an awful lot of stuff as one chunk. So we've taken some of the functionality in Borg and sort of broken out into multiple separate microservices. So the idea of keeping the number of replicas of a pod fixed to some target you've given it is a separate microservice in the Kubernetes world, whereas in Borg it's all buried as part of the scheduler. And then two more thoughts. One is about services. So we built a support for jobs inside Borg, but we didn't really do the next level of support, which was for groups of jobs that are collaborating to provide one thing. And Kubernetes has a much better set of facilities to do that. But one thing we did take away from Borg, and we've applied to Kubernetes as well, is actually scale is not that frightening. If we can service, like I said, a medium-sized cell is 10,000 machines, and these machines have quite a lot of cores in them these days, and we have ones which are much larger. If we can service that, the scale that Kubernetes is targeting, don't worry, centralized solutions work just fine. So those are things we took forward from Kubernetes and applied them. And then one thing that's obviously different is that Kubernetes is being developed completely in the open source world, right? So everything that's being done is out there. We have, I think, 400 contributors at the last count, and lots of people participating in, and this is just great.
Yeah, I wanted to touch on that a bit. There have been, over the years, there have been a number of papers that have come out of Google that have described various internal tools that have then spawned open source clones of those tools by developers outside of Google. For example, MapReduce or Bigtable or Chubby all have kind of open source clones that were developed by people outside of Google. Although Google makes a lot of open source contributions, we mentioned the whole underpinnings of containers and whatnot as just one tiny example. Kubernetes seems like the first time that Google is doing their own open source clone, if you will, or next version. Is there a particular reason for that?
I think actually you touched on it earlier, right? We've seen people take our ideas and run with them and come up with systems that are, although very useful to people, they're not quite what we had available internally. They don't necessarily always include the lessons that we had learned the hard way from building the first systems. And people will relearn them, but sometimes that takes a while. So what we thought here was that we could actually jumpstart that process by contributing a bunch of our expertise from our experience and sort of make that available to people in the outside world in a way that we couldn't do. We can't just open source our internal systems. They're just so interconnected with the rest of our ecosystem internally. But this is a way where we could sort of give people a leg up on making these things usable and available. We're not the first people to have been doing stuff in this space, right? There's plenty of people who've been doing things in the VM world. We have folk like Mesos and other people who've done systems like this, but this is sort of our slant on that stuff. It's a way for us to expose the lessons that we have found helpful in making our developers more productive. We think that's a good thing to bring to the community. And, it turns out we also have a cloud business, and this is a way for us to provide perhaps a way of encouraging people to be more aware of that and take advantage of it where it makes sense.
So I could use Kubernetes if I were running on the Google, a number of containers on the Google Cloud.
Yes, in fact, a couple of different ways, right? You can run Kubernetes in-house on bare metal. You can do it yourself just with raw machines. You can run it on Google Compute Engine and various other people's virtual machine suppliers. And we also provide what we call a hosted version of Kubernetes, Google Container Engine, where we run all of the sort of mastery stuff for you, and you just say, hey, great, create me one of these things, and then I'm going to submit pods to it to get them scheduled. So we just sort of take even one level further of support because we run a version of Kubernetes on your behalf and manage it for you. So all of those things are available to you, whichever makes the most sense.
Is Kubernetes a second system as defined by Fred Brooks?
Yeah, I think we got that out of our system with Omega. which was probably the second system. And I actually gave talks about Omega warning people, this is a prototype, and there are some flavors of it which are a little bit second system-y like. We learned a lot from Omega. In fact, many of those ideas are now being folded into Borg, right? So Borg now supports multiple different schedulers, which is an idea that we floated with Omega and tested out and demonstrated actually worked pretty well. And there's a few other things like that. Some of the other ideas that came out of Omega actually went directly into Kubernetes. So it had a very beneficial effect in terms of idea generation. So we're now realizing, which parts work well, which parts don't. Most of the things that don't work were not because they didn't work. It was questions about what the right trade-off is to make in terms of adoption. And you may have many, many users who are already built interfaces on top of the old system, and then ask them to move to a new one turned out to be harder than we had anticipated. So we're trying to avoid some of those mistakes. Again, let's learn from the things that we've done in the Omega universe and try to bring them to Kubernetes. So Kubernetes is a much more granular system. It has sort of microservices. Partly that was an Omega thing, but we've actually made them much more explicit. We're trying to provide APIs so you can bring your own when you need to. We're trying to make it possible and encourage people to try that. So we're trying very hard to bring forward the things that actually have incredible value and leave behind the stuff that were just more experimental ideas that aren't necessary to get the ideas out. We can come back to them later and add them in once we got the basic framework right, but we don't need them to get the basic system up and going.
Okay, so Omega is the cursed second system, and Kubernetes is the third system where everything's right.
You could try counting that way. Some people argue that there were predecessors to Borg that would suggest that Borg was itself a second system, but let's not go down that path too far.
Okay, fair enough. And we're recording here in the fall of 2015. Kubernetes is production ready at this point in time and released?
Indeed so. We pushed out a version 1, which was the formal one where we started providing version control over the APIs. That came out in July. And as we're recording this, we're in the process of pushing out version 1.1.
Excellent. You mentioned Mesos in terms of other cluster managers that are out there. We had an episode of the podcast, number 243, on Mesos. How does Kubernetes compare with Mesos or work with it?
So let me first start out by saying Mesos was being developed at a roughly similar time to Omega. It was being done by a lot of people from the University of California in Berkeley. So we actually collaborated, we shared ideas. In particular, we would have them come down and talk to us about their latest ideas in Mesos. And we'd go, great, have you thought about the following issues? And basically share problem statements with them. Until their heads exploded and they went back to Berkeley to think about them some more. So there's a lot of overlap in ideas and cross-fertilization, which is a wonderful thing from the research side. On the practical side, Mesos and Kubernetes, in my mind, actually complement each other very nicely. If you have a greenfield site where you like the container models or the Docker way of doing business, and you want to get something up and running, you don't have anything, you could just run Kubernetes on bare metal, and it's great, and we'll do a bunch of stuff. But if you're in a world where you actually already have multiple different kinds of applications and they're sharing resources using Mesos, that's also fine because Mesos supports Kubernetes as one of its frameworks. So you can actually have Kubernetes running on Mesos on premises. You could then have Kubernetes applications running either on premises on raw metal or on Mesos or in the cloud. So that way you actually get the best of both worlds with a single API where you write, if you sort of write the Kubernetes stuff, you'll get that however it's being supported in the next level down. So Mesos, as of today, it's more sophisticated in a few aspects, but for example, some of its scheduling has been out for longer than Kubernetes. Kubernetes is very young. Mesos has been around for quite a few years longer. As a result, it's made advances in some areas, and if you want to benefit from those, you can do so by running on top of a Mesos framework. Our goal, frankly, is to try and help Kubernetes catch up, but in the meantime, they work together extremely nicely. And I think in the long run, there may always be applications where you want to have something like a Spark ecosystem at the same time as you have a Kubernetes ecosystem, and you want them to share the same resources, in which case a Mesos-like solution is a pretty good way to go.
Okay, so if I had my fleet of machines and I'm running them with Mesos, and maybe I've got Hadoop in there or Spark, and now I want to do some other things that don't fit into that model and I want to run them under Kubernetes, I can just put in Kubernetes as another tenant framework in my Mesos cluster?
Exactly. And our goal is to try and, as Kubernetes evolves and as more people start contributing to it, we'd like to try and move some of those other frameworks to be hosted on top of Kubernetes. So if you don't have a Mesos environment, you could still run things like Spark or Hadoop. There's no reason why they couldn't be moved onto that world. They just run containers after all, so we think they could fit in. It's long-term plans. So
I could run Mesos on my Kubernetes and then Hadoop on my Mesos.
I suppose you could. Try it. See, let me know how it goes.
Okay. So, kind of winding things up here, are there any items that we didn't cover that you think our listeners would like to know about?
Almost certainly yes, but I would point people to the Borg paper. There's actually quite a lot of information in there. People occasionally accuse me of putting too much stuff in there, so it's sometimes... But that's fine. I mean, I'd rather have that accusation than not having enough. So there are many topics in there we didn't get a chance to talk about. That will also give you a chance to look at some numbers, some of the evaluations we did, and then there's a bit more in-depth comparison than we had time for here today between what we learned about Borg and Kubernetes and how we bring those ideas forwards. So yeah, probably that's a good place probably a good resource to look at.
Right. We'll certainly have a link to the paper in the show notes. Are there any links for your presence online that you would like us to include? Or how can people get in touch with you or follow you?
They're welcome to have access to my website. I'll make sure you have the link and put that in the show notes too. That has a list of my papers and it's got things like my email address and contact information.
Like I said, we'll have links to all of that in the show notes for the episode. John, I'd like to thank you for being on the show.
Thank you very much. I've really enjoyed this.
I'd also like to thank Jeff Meyerson and Sven Johan, fellow hosts on the show, who started the ball rolling on this episode. This is Charles Anderson for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE-Radio, or search for the Software Engineering Radio group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.